Welcome to the Unit 4, Section 2 video on solutions of polynomial equations. So this unit, or I should say this section, is going to be divided into two parts. The first part, I'm kind of going to go over a little bit about polynomial functions of higher orders and just kind of talk about where this fits in the big scheme of things. And I'm also going to talk about 4 different methods of factoring that you can use on higher order polynomials to kind of break things down a little bit. The second half of this section is going to be very example based. It's going to be just several examples showing you how those 4 methods work and then what you do once you use those 4 methods to solve equations. So let's start off by talking about polynomial functions. So far we have explored constant, linear, quadratic, and cubic functions. These are all types of polynomial functions. Okay, so we have been working with polynomials for quite a while now. We just haven't quite used the name polynomial functions, at least not exclusively. We've been talking about linear functions and quadratic functions and cubic functions, but these are all polynomial functions. They're all types of polynomial functions. And you can see the ones that we've covered so far here in this kind of list here. So let's start from the top here. Let's start with cubic functions. What is the degree of a cubic function? Or, in other words, what's the highest power of a cubic function? Well, that would be 3. For a quadratic function, the highest power was 2. For a linear function, the highest power is 1. And then for a constant function, the highest power is 0 because you don't have any variables. It's simply y equals 5, y equals 4, or in this case, on the graph that you're seeing, y equals -3. All right, well, how many times does the constant function hit the x-axis? Well, you can see that it parallels the x-axis and it never crosses it. So you would have no zeros. You would have no roots. For a linear function, it hits 1 time. For a quadratic function, it hits twice. And for a cubic function, it hits 3 times. Or at the very least, it will hit at most 3 times. Okay, and that's going to be the case for all of these. The most times it can hit the x-axis is the highest degree, or the highest power, which would be your degree of your polynomial. Okay, so note that polynomial functions are not merely limited to constant, linear, quadratic, or cubic. You can have a function with x to the 4th, x to the 5th, x to the 6th, and so on. In each case, the maximum number of zeros is also the degree of the polynomial. Now, can we have fewer than the degree of the polynomial for our solutions or our zeros? Well, let's take a look at that. So here we're going to talk about the fundamental theorem of algebra. So we found that the highest number of solutions we can have is the degree. Well, when we talked about quadratic functions, we found that there could be 2 real solutions, 1 real solution, or 2 imaginary solutions, which you can see graphed here at the bottom. Now, recall that when a quadratic function does not cross the x-axis, there are no real solutions. And you can see that clearly in this graph. The whole thing sits above the x-axis, so it never crosses. However, there are imaginary solutions. So because we do have imaginary solutions, the most we can have in a quadratic are 2. The least number of solutions we can have is 1. And that pulls us into the fundamental theorem of algebra. When you count all numbers, all types of numbers, including any complex number, complex numbers include imaginary numbers and real numbers, then the least number of solutions you can have is 1. The greatest number of solutions you can have is whatever the degree of your polynomial is. So if you have x to the 3rd as your highest power, then the most you can have is 3, but the least you can have will always be 1. So the set of complex numbers includes all numbers, real and imaginary. So let's just talk about what complex numbers are very briefly. So I have here a set of nested boxes, and we're going to use this to describe how all the numbers are related. So any number you can think of, real or imaginary, that's a complex number. And we denote that with a C, with a slash, kind of vertical slash on the inside of it. We write it that way because we can't write in bold. If you look in text, you'll see these letters in bold, but since we can't write in bold, we kind of make do with our own notation when we handwrite these things. Now, in the complex numbers in this set, it's made up of two different types of numbers, some that are on this side and some are on this side, and they are exclusive. So there's no blending of these numbers. You can have either imaginary numbers and that is indicated by a double striked I. And then you can have real numbers, and then you're more familiar with this notation, a double striked R, for all real numbers. Okay, imaginary numbers are made up of things like 3 plus 2i. There's an I in here, so that makes it imaginary. I square root of 3 is an imaginary number. I on its own is an imaginary number. Real numbers are made up of anything that doesn't have an I in it. So 3 is a real number. 1/4 is a real number. 6.385 is a real number. Pi is a real number. Okay? Those are all real numbers. But within real numbers, we have specific types. Part of the real numbers are rational numbers. And they are indicated by a Q with a slash on the inside, similar to how we did the C. Okay? Rational numbers are any number that can be written as a fraction. So 2 would be a rational number because it's 2 over 1. A fraction, such as 1/3, would be a rational number. We would have 8.613. That's a rational number because that can also be written as a fraction. 1/3 has a repeating decimal forever, but the decimal repeats. So if you have a number, say like 7.23 repeating, then that can be written as a fraction as well. It's only when you have a number that's a decimal that doesn't repeat, it goes on forever without repeating, that's when you have an irrational number. So that would not be a rational number, and pi is an example of that. All right, within the set of rational numbers, we have integers. And integers are represented by a double slashed z. Let me try to write that a little bit nicer. A double slashed z. Not sure that's much better, but you get the idea. So integers are basically your whole numbers, negative and positive, and it includes 0. So you could come from negative infinity and go to -3, -2, -1, 0, 1, 2, 3, and it continues on forever. And then within the integers, you have your natural numbers. And natural numbers are often also called your counting numbers. And they're represented by a double slashed n. So they're your numbers that start with 1 and go on 2, 3, on forever. So this kind of gives you an idea of how numbers are broken down, a little refresher on that for some of you. Complex numbers include all numbers, real and imaginary. And so that's the type of solutions we're going to be looking for. Now, before we get into solving higher order polynomials, we need to talk a little bit about factoring. So to factor higher degree polynomials, we're going to go over some new factoring techniques here. Let's first review some of the techniques we learned in the last unit. So we've already learned how to factor and solve quadratic equations by applying the zero product property. If you have a few things that are multiplied by each other and it all equals 0, then one of those things that's being multiplied has to be 0 itself. And we factored the quadratic, got it down into factored form, and then set those pieces equal to 0. And we used all kinds of different techniques. Greatest common factor is always used first. We want to see what we can factor out before we do anything else. And then we utilize quadratic trinomials, both with the leading coefficient of 1 and not being 1. Difference of squares, perfect square trinomials, all factoring techniques that we have used and you're going to continue to use. But to solve higher order polynomials, we're going to need a few other techniques as well. So we're going to focus on 4 new techniques. Factoring by grouping, which really is not that new of a technique. It's something that we've already used within the context of factoring a trinomial with a leading coefficient greater than 1. So we'll briefly hit that. Then we've got the sum of cubes and the difference of cubes, which are formulas here that you're just going to have to remember, okay? And then we also have solving by quadratic form, factoring by using quadratic form. So let's start off by talking about factoring by grouping. So when we do factoring by grouping, you're going to factor out the greatest common factor of the first 2 terms. You'll factor out the greatest common factor of the second 2 terms. And then the greatest common factors make up one binomial in factored form. And then those identical binomials will make up the other binomial in factored form. So the easiest way to show it is by doing an example. So in this example, we're going to factor the first 2 terms. So what we can pull out is an 8x squared, because that's the biggest thing we can pull out of those first 2 terms. In the first term, that leaves an x, and in the second term, that's going to leave a positive 3. Well, we know we want an identical x plus 3 over here. So what can we pull out of these second 2 terms to make this happen? We can pull out a positive 5. And then we just factor out our x plus 3, and then we're left with 8x squared plus 5. And now that's factored. In the second example, we are going to pull out of the first 2 terms 7x squared. That leaves in the first term an 8x, and then that leaves behind a 1 in the other term. Now we know we want 8x minus 1 here, so what do we pull out here to make this happen? A negative 1. And so 8x minus 1 is the common term in both of these, and what's left over is 7x squared minus 1. So that's how factoring by grouping works. For a sum of cubes, we are going to use this form. Okay, a cubed plus b cubed equals a plus b times a squared minus ab plus b squared. So these will only require one line of work if you know how it works, okay? So first, we take what x cubed, we take the cube root of that. So the cube root of x cubed is x. The cube root of 64 is 4, because 4 times 4 times 4 is 64. And then we're going to use our a and b to do the rest. So a squared is x squared, minus ab is x times 4, which is 4x. And then b squared is 4 squared, which is 16. And that is factored. Down here, the cube root of 8 is 2. The cube root of x cubed is x. The cube root of 125 is 5. And now we're going to use those terms to do the rest. 2x quantity squared is 4x squared. Then we combine the two, so we have minus 10x. And then 5 squared is 25. And that one's now factored. Now take a look at the difference of cubes here at the bottom. It's the same format. The only change is, instead of leading with the positive, because now we're not doing the sum, we lead with the negative because we're doing a difference. And then we swap the first sign in our trinomial. So everything's added in the trinomial this time for the difference of cubes. So let's do a couple of examples of the difference of cubes. So again, just take the cube root of x to the third, which will be x. Take the cube root of 8, which is 2. And then we do x squared plus 2x plus 4. For the next one, take the cube root of 27, which is 3, the cube root of x cubed, which is x, the cube root of 8 is still 2. And then we do 3x quantity squared, which is 9x squared. Then we do AB, which is 6x. And then we do 2 squared, which is 4. So as long as you can remember the form, sum and difference of cubes really is not that difficult. And then the last form we're going to talk about is quadratic form. Okay, in quadratic form, you're going to use the factoring technique that you would use for a quadratic factoring. You're going to use that same technique because this is formatted kind of the same way. Okay, so a quadratic trinomial has x squared plus bx plus c, which factors into x plus something times x plus something. If we have a degree 4 trinomial, that's x to the fourth plus bx squared plus c. Notice that the x squared goes to x to the fourth, so we doubled the square. And then our x goes to x squared, so we doubled that 1 power to 2. So since everything kind of works consistently through here, we can now factor this as x squared plus something times x squared plus something. So let's do this as if these are quadratics. We just have to remember to put the correct power on our x. So in example 7, we're going to factor this as we traditionally would. We want to find two numbers that multiply to give us 14 and add to give us negative 9. And those factors are negative 2 and negative 7. So instead of x minus 2 times x minus 7, you're going to do, because we have an x to the fourth here, you're going to do x squared minus 2 times x squared minus 7. And that would be your factored form. For example 8, we can recognize this as a difference of squares. And you can recognize that outright because x to the fourth is just x squared squared. So you take the square root of the first, which is 4x squared, minus the square root of the second, which is 5, plus the square root of the first, plus the square root of the second. And now that is factored. And then finally, in this last one, we can recognize this as a perfect square trinomial. Because 9 times 4 is 36. The square root of 36 is 6. 6 times 2 is 12, which is our middle term. So this is a perfect square trinomial, which means you can take the square root of the first term, which is 3x squared, the sign of the second term, which is plus, the square root of the last term, which is 2, and square it. And now we have factored example 9. So now that we have used these new techniques and we've gotten a little bit of an introduction to these new techniques, let's move on to solving polynomial equations by factoring, which means we're going to take a higher order polynomial that's set equal to 0, and we're going to solve it all the way down to our x values. And a lot of this is going to utilize, in the later steps, what we did in Unit 3. So let's start off with example 10 here. If we were going to factor this, well, we've got 4 terms. When you see 4 terms, the first thing you should think is grouping. Before you do anything, let's see if there's anything we can factor out of all of that. And it turns out there's nothing, because this 6 stands alone. The rest have x's in it, but there's no x in this last term. So there's nothing really we can factor out from the start. So 4 terms, let's factor by grouping. What can we factor out of the first 2 terms? An x squared. And that's going to leave us with an x plus 3. Well, we know we want to get an x plus 3 on the other end. So what do we pull out of these 2 terms to make that happen? A plus 2. And so we end up with x plus 3 times x squared plus 2 equals 0. Now, the next question we ask is, can we factor either of those terms? Well, x plus 3 is as far as we can go with that. And we cannot factor x squared plus 2. Once you get to the point where you cannot factor anymore, then you're going to set your terms equal to 0. So we've got x plus 3 equal to 0, and we've got x squared plus 2 equal to 0. The first one's easy. We've got x equals negative 3. The other one, we've got x squared is equal to negative 2, and then we take the square root of each side, and that gives us plus or minus the square root of negative 2. And we simplify the radical, which gives us plus or minus I square root of 2. So we have our 3 solutions. Positive I square root of 2, negative I square root of 2, and then negative 3 over here. The highest degree is 3, so at most we're expecting 3 answers, and 3 answers is what we got. Now, 2 of those answers are imaginary, so keep in mind, if you were to graph this function, you would only see it cross the x-axis one time, and that's at x equals negative 3, because you will not see it cross the x-axis for these imaginary solutions. So it only crosses the x-axis at the real solutions. All right, let's move on to example 11. Example 11, again, this is going to be a factoring by grouping situation. So we factor out the first 2 terms an x squared. That leaves us with an x plus 1. We know we want an x plus 1 over here. So to make that happen, we're going to factor out a negative 5. And so that gives us x plus 1 times x squared minus 5 equals 0. We can't factor either of those any further, so we're going to set them both equal to 0 independently, so we can solve for our values of x. Over here we get x equals negative 1, and then in the other one we get x squared equals positive 5. So x equals plus or minus the square root of 5. For example 12, we're going to look at this and recognize it as a difference of cubes. So since it's a difference of cubes, we're going to use that new technique that we learned. We're going to take the cube root of the first, subtract the cube root of the second, which is 2. And then we've got a squared, which is x squared, plus 2 times x, which is 2x, plus 2 squared, which is 4. Now at this point, we cannot factor either of these, so we're going to break them up. So we got x minus 2 equals 0. Let's go ahead and solve that one. X equals 2. That was easy enough. Let's go and set the other one equal to 0. This is where you're going to come into using some of the techniques from Unit 3. We can't factor that, so what we're going to have to do is either complete the square or use the quadratic formula. I'm opting, since we don't have a leading coefficient, to complete the square. So we're going to have x squared plus 2x. We're going to move the 4 to the other side. Now we're going to complete the square. So we take half of the x term, so that's going to be 1. 1 squared is 4, or 1 squared is 1, I should say. So we're going to add 1 to each side. Since we made this a perfect square trinomial, we can factor it by taking the square root of the first, the sine of the middle, and the square root of the last, and squaring it. And then negative 4 plus 1 gives us negative 3. We take the square root of each side, and we get x plus 1 equals the square root of negative 3, plus or minus, of course. And then x equals negative 1 plus or minus. Simplify the square root, you get I square root of 3. So, one real solution, two imaginary solutions, three solutions overall, which is the most we can have. Example 13 is a sum of cubes. So very similarly, we are going to solve this as such. Cube root of the first plus the cube root of the second. Then we have our a squared minus ab, which is 4x, plus b squared, which is 16. At this point, we cannot simplify or factor anything else, so we're going to set them both equal to 0. The first one is easy enough to solve, x equals negative 4. The other one, I'm going to again opt for completing the square. So we've got negative 16 here. Half of 4 is 2. 2 squared is 4. So we're adding 4 to each side. And then square root of the first, sine of the middle, square root of the second to factor it. This gives us negative 12 on this side. Take the square root of each side. And we have x equals 2 plus or minus, and when we simplify this, we end up with 2i square root of 3. All right, the next example. Let's take a look at what our polynomial looks like. We've got three terms. We've got an x to the fourth, an x squared, and then one without an x. So this very much looks like we can use quadratic form. So let's try quadratic form on this one. Find two numbers that multiply to give us negative 12 and add to give us 1. Those factors are 4 and negative 3. So we've got x squared plus 4 times x squared minus 3 equals 0. We can't factor either of those any further, so we're going to have x squared plus 4 equals 0. And we're going to have x squared minus 3 equal to 0. Let's solve this first one. X squared equals negative 4. Take the square root of each side, and you get plus or minus 2i. On this one, we got x squared equals 3. You take the square root of both sides, you get x equals plus or minus the square root of 3. The highest power in this polynomial was 4, and we ended up with 4 answers. Two of our answers are positive 2i and negative 2i, and the other two answers are positive square root of 3 and negative square root of 3. So altogether we have 4 answers. 2 imaginary, 2 real. Example 15 also looks like a quadratic form. We got 3 terms. So let's factor this. Two numbers that multiply to give us 54, add to give us negative 15. Those factors are x squared minus 9 and x squared minus 6. So minus 9 and minus 6 are the factors that we use here. Now, can we factor either of those? Well, look at the first one. We can factor this because this is a difference of squares. So since it's a difference of squares, I'm going to factor it down to x minus 3 times x plus 3. And then the second one we cannot factor, so we will just leave that alone. And now we've factored it as much as we can. We're going to set all of these equal to 0. First one, we get x equals 3. On the second one, we get x equals negative 3. And on the third one, we get x squared equals 6. And we take the square root of each side. It gives us x equals plus or minus square root of 6. So our highest power is 4. And we indeed have 4 answers. And in this case, they're all real. So that means that this particular function will cross the x-axis all 4 times. All right, on to example 16. So this one, let's look at our first 2 terms, or our only 2 terms. Before we do anything else, we always want to check, is there something we can factor out at the start? And in this case, there is. We can factor out an x squared. And that leaves us with a 64x to the third plus 27. Well, now we can factor this because this is a sum of cubes. So the x squared is going to come along for the ride. Don't forget to leave that out. Cube root of 64 is 4. The cube root of x cubed is x. The cube root of 27 is 3. And then we use this a and the b to give us the rest. So we got 16x squared minus 12x, and then 3 squared is 9. Well, at this point, we can't factor anything else, nor do I really care to factor this or even attempt it. So let's go ahead and split everything up. We've got x squared equals 0. We've got 4x plus 3 equals 0. And then we've got 16x squared minus 12x plus 9 equals 0. Well, the first 2 are easy enough to do. We end up with x equals 0. And in this case, 2 of the x's ended up being 0. So we're actually going to end up with fewer than 5 solutions for this particular equation. Remember, we don't have to have 5. It can be fewer than 5, but we have to have at least 1. And in this case, we are going to end up with 4 solutions instead of 5 because one x is 0, the other x is 0, and they're identical. For this one, we just subtract 3, and then we divide by 4, so another x value is going to be negative 3/4. Now let's take a look at this last one. We don't really want to factor it. We can't take the square root because of that x, nor do I really want to complete the square because we've got that 16 out in front. We'd have to divide everything by 16. And we could complete the square, that would work, but we would be dealing with quite a few fractions. So I think at this point, it would be easier to utilize the quadratic formula. So x equals the opposite of b, so we got negative 12 plus or minus the square root of b squared minus 4ac all over 2a. So we've got 12 plus or minus. When you do the math under the square root, you end up with negative 432. So the discriminant's negative. That means we're going to have some imaginary solutions. And then 2 times 16 is 32. Let's continue to clean up a little bit. If we simplify that radical, we're going to end up with 12i square root of 3. And then we can reduce down our fraction. And so we end up with x equals 3 plus or minus 3i square root of 3 over 8. And so 2 of our solutions are here, and then our third and fourth solution are the ones we already found. So 4 solutions overall, 2 that actually cross the x-axis, and then 2 that are imaginary. All right, on to example 17. So again, the first thing you want to do is see if there's anything you can factor out, and there indeed is. We can factor an x out, and that's going to leave us with 27x to the third minus 8 equals 0. Well, this is a difference of cubes, so that front x is going to hang out. We got 27. Cube root of 27 is 3. Cube root of x cubed is x. Cube root of 8 is 2. And then we're going to square the a, so that's 9x squared plus 6x plus 4. And at this point, we're going to split everything up because we have factored as far as we can. X equals 0, that's already a solution, so we're good there. 3x minus 2 equals 0. Let's go ahead and solve that one. 3x equals 2, and then divide by 3, so x equals 2/3 is going to be a solution. And then finally, we've got 9x squared plus 6x plus 4 equals 0. Again, not a big fan of completing the square here because we have to divide by 9 and we're going to end up with a lot of fractions to work with. So let's use the quadratic formula again. X equals the opposite of b plus or minus the square root of b squared minus 4ac all over 2a. And what we're going to get is negative 6 plus or minus the square root of negative 108 over 18. So I'm going to go ahead and go this way with it here. We got negative 6. You simplify that radical, you end up with 6i square root of 3 over 18. And that does reduce down. So you do end up with 1, or I should say negative 1, plus or minus I square root of 3 over 3. So, two imaginary solutions again, two real solutions. Highest power in this one was 4, and we did end up with 4 solutions overall. But because only 2 of those solutions are real, we are only going to have this function cross the x-axis twice. All right, for example 18, let's take a look at this function. Everything has an x in it, and if you look at all the coefficients, all those coefficients are divisible by 3. So we're going to pull a 3x out, and that's going to leave 7x to the third plus 8x squared plus 14x plus 16. Now this part that's left has 4 terms in it. So when you see 4 terms, again, think grouping. So we've got 3x. I'm going to use a bracket here. What can we factor out of the first 2 terms? We can factor out an x squared, which leaves us with 7x plus 8. We know we want a 7x plus 8 out of the other one as well. And what do we factor out to make that happen? Plus 2. And so we end up with 3x times 7x plus 8 times x squared plus 2 equals 0. And we look at what we've got left. We cannot factor anything. So there's nothing more for us to do but to set everything equal to 0. So the first one, divide both sides by 3, x equals 0. Subtract 8 on this one, and divide by 7, and you get negative 8/7. And then for this one, subtract each side by 2. In fact, that would give us negative 2 on that side. And then take the square root of each side, and you get plus or minus I square root of 2. So 2 imaginary solutions, 2 real solutions. For example 19, there's nothing we can factor out from the start, but we do have 4 terms, so let's think grouping. So what can we factor out of the first 2 terms? X to the 4th. That leaves behind an x squared plus 2. We know we want an x squared plus 2 over here. And so what do we factor out to make that happen? A negative 1. So we end up with x squared plus 2 times x to the fourth minus 1. Can we factor either of these? Well, the answer is yes, we can. The x to the fourth minus 1 is a difference of squares. So the x squared plus 2 comes along for the ride. X to the fourth minus 1 factors into x squared plus 1, x squared minus 1. Now, can we factor any of these? Well, x squared minus 1 is a difference of squares again. So we got x squared plus 2 times x squared plus 1. And we factor this one down to x plus 1, x minus 1. And now we have done all the factoring we can. We'd split it up. X squared plus 2 equals 0. X squared plus 1 equals 0. X plus 1 equals 0. X minus 1 equals 0. So we subtract 2 from each side on the first one, and we get x equals plus or minus I squared root of 2. We subtract 1 from each side on the next one, and we take the square root of each side, and we get plus or minus I. And then this one, we subtract 1, we get x equals negative 1, add 1 on this one, we get x equals 1. So the highest power in this one was 6. We'd expect at most 6 answers, and that's what we got. We got 2 real solutions and 4 imaginary solutions. All right, let's take a look at example 20. We're going to factor and solve this one. So we've got a trinomial. Let's think quadratic form. 2 numbers that multiply to give us 36, add to give us negative 13. And that happens to be negative 9 and negative 4. So we factor it as such, x squared minus 9 times x squared minus 4. Well, can we factor these? Well, we can actually factor both of them. They're both differences of squares, so let's factor the first one. You get x plus 3 times x minus 3. In this one, we get x plus 2 times x minus 2. And now we've done all the factoring we can. We're going to set each piece equal to 0. X plus 3 equals 0. X minus 3 equals 0. X plus 2 equals 0. And x minus 2 equals 0. So x equals negative 3. X equals positive 3. X equals negative 2. And x equals positive 2. Highest power is 4. We got 4 solutions, and we got 4 real solutions. All right, this is the last example for this section. We're going to factor and solve this one. Well, the first thing we need to do is let's pull out an x. That leaves us with x to the 6th minus x to the 4th minus 9x squared plus 9. We've got 4 terms here, so factor by grouping should be the thing that comes to mind. So we factor out of the first 2 and x to the 4th. That leaves an x squared minus 1. And these 2 terms, we're going to factor out a, well, we're going to factor out a minus 9. And that's going to give us an x squared minus 1 again. All right, to finish off the factoring by grouping, we've got x squared minus 1 times x to the 4th minus 9. Well, we do have more factoring to do because x squared minus 1 is a difference of squares, so let's factor that. We have x plus 1 times x minus 1. X to the 4th minus 9 is also a difference of squares, so we've got x squared plus 3, x squared minus 3. We are done factoring. There's no more factoring to do. So let's set each of these pieces equal to 0. Well, the first one gives us a solution right away. X equals 0. X plus 1 equals 0. x minus 1 equals 0, x squared plus 3 equals 0, and x squared minus 3 equals 0. So x equals negative 1, x equals positive 1. On these other two, we've got x squared equals negative 3. Take the square root of each side, and you're going to end up with plus or minus I squared root of 3. And then on this one, x squared equals 3, so x equals plus or minus the square root of 3. So our highest power in this one is 7. We would expect to get 7 solutions at the most, and that's how many we ended up with. 3 real solutions, 5 real solutions, and 2 imaginary solutions. So this function, when graphed, will cross the x-axis 5 times, once for each real solution. The other 2 solutions are imaginary. Okay, so this wraps up Section 2 of Unit 4. As we move into Section 3, we're going to get into some of the key features of higher order polynomials.